In this video, we're going to look at covariance and correlation coefficient. When we look at covariance, we're looking at a property that is similar to variance for one random variable, but we're looking at it in terms of two random variables, and therefore it's called covariance. So we have two random variables, x and y, and the covariance is defined as the expected value, which we'll define it in terms of the expected value of x minus mu x, or the mean of x, times y minus the mean of y. Since we have this expected value operator, we can reduce this somewhat. We do this multiplication, multiply through, notice we'll have x times y minus x times mu y minus y times mu x, and then plus x, or mu x times mu y. Now, since this is a expected value operator and it's linear, we can take the expected value of each of these individual items. So we'll have the expected value of xy. We'll also have the expected value of x times mu y. This is a constant, so we can pull that out. So we'll have the expected value of x times mu y. Also, mu x is a constant, so we'll have minus the expected value of y times mu x. And then since mu x times mu y is a constant, we just have it by itself. Now remember, the expected value of x is equal to mu x, and the expected value of y is equal to mu y. So if we make those two substitutions, notice that we'll have a negative mu x times mu y, another negative mu x times mu y, and then a positive mu x times mu y. So two of those will cancel, and we'll end up with just the expected value of x times y minus mu x times mu y. So just like we had with the variance of one random variable, we had two ways of looking at it. So we have the same thing here. We've got the covariance of x and y is this multiplication with the x minus mu x times y minus mu y, or the expected value of x times y minus mu x times mu y. Alright, so since we have those two methods of showing it, we also have, again, two methods of doing the calculation. Since we're looking at covariance, or two random variables at the same time, we have to do the definition in terms of the joint distribution function. Now we have two random variables, and we're going to just define it in this case for discrete random variables. So x and y are both discrete random variables. X has n values and y has m values. So for this definition, since we're doing the expected value, we're going to put the values in our summation for what's inside here. So we'll have an x sub I minus mu x term times y sub I, or y sub j, minus mu y, all times our distribution function, or our joint distribution function. Now, since we have two variables, x and y, and this is a two-dimensional function, we have to do a double summation. So we have to sum over all of our x values and sum over all of our y values. So it's a double summation. So we can do this calculation where we subtract the mean of x from all of those x values and the mean of y from all of those values, and then do this multiplication and sum. Or we can do this second term, the second calculation, where we have the expected value of x times y minus mu x times mu y. So the calculation for the expected value of x times y, we have x times y inside the expected value. So over here in our double summation, we'll have x times y. So each of our x values times each of our y values times their corresponding joint distribution value. And then we'll sum all those up. Sum up over all of our x values and sum up over all of our y values. So again, a double summation. But the difference here is we're not having to subtract the means for each one of these values. Now, once we get done with this calculation, we plug that back into here and subtract off mu x times mu y, and we have our covariance. Alright, so here's an example. This part here is a problem we've done in a different video, and let's suppose this is our joint distribution function, and we have our marginal for x and our marginal function for y. So let's calculate the covariance for these x and y random variables. I'm going to use the easier one, or which one I think is easier, expected value of x times y minus mu x times mu y. Right, the first thing we got to do is find the mean for x and the mean for y. I'm not really going to spend much time on that. We've done that before, but we're going to use the x values times our distribution function for x and our y values times our distribution function for y, and sum all those up. So let's say for the y, we'll have 1 times that plus 2 times that, and so on. That's how we'll get the mean for y. And you see those values here. The mean of x is 4/3, and the mean of y is 161 over 36. Okay, now that if we're looking back up here, we've got the means that we need. Now we need to calculate this expected value. To calculate that expected value, again, we're going to do a double, or in this case, we're going to do a double sum. And we're going to take each x value and y value and multiply times its distribution function value. Now I've done essentially 3 rows here for the calculation. Let me go back to the distribution function. Let's look at how that's done. Okay, so here's our distribution function. We're going to take each x value, each y value, and its distribution value and multiply them. And then we're going to sum them all up. So we'll have 0 times 1 times 1/36 plus 0 times 2 times 3/36 plus 0 times 3 times 0. Do that for all of those values. Then on the next row we'll have 1 times 1 times 0 plus 1 times 2 times 0 plus 1 times 3 times 4/36. We'll do that for that row and then for the final row. So we're going to have to do it for all of these values. So we'll have 3 times 6, or 18 values that we have to sum up. 18 values that we have to multiply all the corresponding values and then sum them all up. So I've got 6 on this row plus the 6 on this row plus the 6 on this row. Summing all those up, we'll end up with 59/9. So that's the expected value of x times y. Now, just like for the variance, don't forget to go back and do that final calculation for the covariance. We want to put that value we just calculated in minus the means multiplied. And so we'll have 59/9 minus 4/3 times 161 over 36. Now what we'll find though, with the variance we had to always have a positive value. With the covariance we can actually end up with a negative value. In this case we've got a positive value 16/27. So that's the covariance for those two random variables. Now let's also look at something now called correlation coefficient. Now the covariance that we just got done looking at can be affected by sort of the scale or the size of a random variable. Suppose we just had that same random variable, but we just we multiplied it or changed it by multiplying it by a constant. Changing that or multiplying by a constant really doesn't affect how these are sort of related to each other. It just affects that x value. But if we do that covariance, we can show that the covariance of ax and y is equal to the covariance of x and y times that a value. So by just scaling by a constant, we actually scale that covariance. Really isn't that great of a property. We don't really want that to happen. So we use something called correlation coefficient. Correlation coefficient is really the covariance divided by the standard deviation of x and the standard deviation of y. These two values down here prevent something like this from happening. So if our x changes by a constant, multiplied by a constant, then this correlation coefficient actually doesn't change. So what are the properties for the correlation coefficient? Well, the correlation coefficient of x and y is equal to the coefficient for y and x. We can reverse those. Also, the correlation coefficient for x and x is equal to 1. That's perfect correlation. The x, of course, is related to x perfectly, and so we get 1. Now for x and minus x, we get negative 1. So the range of values, I should have written down, the range of values we can get for the correlation coefficient is between 1 and minus 1. Now if we scale x by a linear scale, or we scale y by a linear scale, we end up not affecting the correlation coefficient at all. So it's invariant to that linear scaling. All right, let's look at the example. We're going to find the correlation coefficient for the function that we were already just looking at in this video. We already found the covariance. It was 16/27. So all we got to do now is find the standard deviation, or the variance, and then the standard deviation for x and y, and then do that calculation for the correlation coefficient. All of this to find the variance of each of these random variables we've done before, but I have it here for completeness. We're going to use the expected value of x squared minus mu x squared. So the mean for each of those we have the mean. So let's calculate the expected value of x squared. So I have 0 squared times the distribution for x at 0, plus 1 squared times that value, plus 2 squared times that value, gives us 20/9. Now we put that back into our equation. 20/9 minus the mean squared. The mean was 4/3. Square that, and we get 4/9. So the variance is the square root of that, which gives us 2/3. We do the same thing for our y variable. There are 6 values for our y variable. I didn't show them all here, but we take the y value times squared times its probability and so on. Sum them all up, we get 791/36. So the variance for y is 791/36 minus its mean squared, and we get 2555/1296. And so the standard deviation is the square root of that. We get the square root of 2555/36. Now the correlation coefficient is just our covariance divided by those two standard deviations. And so I plug those in. You can see what the values are here. And after I do that calculation, I get 0.6331. So what we need to see here is that the value is, in this case it's positive, but it could be negative. The correlation coefficient could be negative, but it will always be between 1 and minus 1. And so in this case we've got 0.6331. If you get something outside that range, you know you've done something wrong. You need to go back and evaluate what you did wrong.